With the principles from our last workshop, let's look at practices on how to put those principles to work. This workshop, like the last, is going to be relatively rapid. We've got about 40 minutes to talk about a topic that should take many days, but we'll cover all the highlights, and of course at the end will be all the references for you to go and chase and put all these topics together and put it to work on your project to increase the probability of success. So we're back again to what the core elements of project risk management are all about. We have to remember, as always, all risk comes from uncertainty, and uncertainty on projects comes in only two forms. Uncertainty that's reducible, that's called epistemic uncertainty. It's the lack of our knowledge, and we can buy more knowledge. We can spend money to create new knowledge, prototypes, testing, redundancies. Epistemology is the study of knowledge, and the other type that's on projects is alleatory. Alea is a single die, 6 sides, that the Greeks used to gamble, and this alleatory uncertainty is natural variance. The weather is alleatory. The productivity of human beings doing their work is alleatory. It's a random process. It's never exactly the same. So those are the two sources of risk that happen on projects, and we'll learn in this workshop how to handle them. And there's a third type, ontological, which is unknown unknowables, and that's always plan B. So we won't talk about those. Those will be something different here. So just a reminder, at least in our complex system of systems world, that we get in trouble when we treat projects as complicated. And in fact, they're complex. So we must operate in the presence of complexity that's created by uncertainties, reducible uncertainty and irreducible uncertainty. And this was an advice from a person who's a fairly well-known systems engineer. This book should be on your shelf if you're a project manager or you're a risk manager. And he speaks about this, that if we plan in the beginning that nothing's going to go wrong, it's definitely going to go wrong because we operate at all times in the presence of uncertainty. The sources of all this risk management and the scope of all this risk management is some high-level words here from a person that I've actually worked with, Ed Conroe. He's at the Association for Aerospace Engineering and the Aerospace Corporation in El Segundo, California. And he was on a program for manned spaceflight that I was with on, and several other deep space programs for NASA. So this is another book that should be on your shelf for effective risk management. But his advice to us here is that all issues have to be identified, they have to be eliminated, we have to manage risk as if it is always there, it never can go away. It's always going to be present on our projects, and there's some good quotes for him. And then just a reminder one more time before we get started on our practices that we cannot actually manage risk. If risk comes from uncertainties, then we can't make those uncertainties go away. Unless you're a deity, you can't make it stop raining. Unless you have a production line with no errors and producing perfect products, you're always going to have uncertainties that create risk. So we have to manage in the presence of uncertainty, and that's our job. So it's not risk management per se, it's managing in the presence of uncertainties that create risk. And here's again a reminder of epistemic and alleatory uncertainties that we need to deal with. And just a reminder of the 4 or the 5 immutable principles of project success. Risk management is number 4. They are ranked by their importance. If we don't know what done looks like, we can't get there. If we don't have a plan to get there, we have no hope of getting there. If we don't have the right resources, we're not going to get there. And then number 4 is if we don't handle the risks with credible risk handling strategies, we're not going to get there. And then of course, if we don't measure progress along the way, it's going to be a problem. So here is a framework that we use in our complex systems world about putting the 4th immutable principle about risk management to work. We're going to have technical risks, we're going to have programmatic risks, and we're going to have business risks. and we're going to have to understand how to manage all those through risk management, and when things go wrong, for issue management. And we can ask the question, what can be improved, and do opportunity management. But I would like to caution you that opportunity management is not positive risk management. There's a paper that will be referenced in the past, again from Ed Conroe, that we just spoke about, that speaks to being very careful about opportunity and risk. Some professional organizations use those as interchangeable ideas, but he would caution us not to do that. So here's a standard loop about risk management. We want to identify the risks, we want to analyze them, we want to have a plan, we want to track those plans, we want to control them and the outcomes, and we want to communicate all that. And we'll see some more details about that. But this idea that risk management is straightforward is essentially not true. We hope we can manage risk. You know, there's a very good sales book called Hope is Not a Strategy. So risk management is a strategy, but it's got to be built on something more than hope. And there can be no single point assessments of cost or schedule or technical performance can be correct, as well as no single point assessment of risk. All the risk is probabilistic and statistical and stochastic in nature. So every number we encounter in our project management world and in especially our risk management world is a probability. And therefore the risk management activities have to deal with this probability. And number one is we've got to communicate at all times to everybody. That's not only stakeholders but also participants in the project management, and certainly on the risk management side. So here is the ISO 31000 definition of risk. It does use the word uncertainty, and it does use the word effect, and that's good. Not all professional project management organizations comply with that. PMI is one. They don't actually speak very well or very clearly about probabilistic or uncertainty as part of their risk management processes. So if you don't have ISO 31000, you can probably find soft copies of that on the web, but that would be good to have in your library about risk management. And before we get started here, let's remind ourselves one more time that all risk comes from uncertainty, and uncertainties are basically things that we can't be certain about. And it's created by our incomplete knowledge. That's the epistemic uncertainty. And it's created by random processes, which is our alleatory uncertainty. So our job as project managers is to manage in the presence of this uncertainty to increase the probability of success. So everything we do in the project and program management world operates in the presence of uncertainties, and those uncertainties always create risk. So what's our real job here as risk managers in our practicum world? It turns out risk management is a very mature process of systems engineering. And systems engineering is about the engineering of systems. And its job is to reduce potential risks to some acceptable level throughout the life of the project or the program. And it's continuous, and it's forward-looking, and it's got to be balanced with the project objectives, because we don't always need a perfect solution. We need a solution that's good enough. So a little phrase we use here in the States is that better is the enemy of good enough. And we've got to decide somehow how to discover what is the unit of measure of good enough, and then apply our activities to those. Let's use the poster child for not doing good risk management. Poor Captain Smith told the world that he could not imagine any conditions in which his ship could be in trouble. No conceivable disaster could ever happen to that ship. It's modern, it's safe, it's everybody get on board, we're going to head back to America. Of course, that was the Titanic, and he was willfully ignorant of the risk of the icebergs in the North Atlantic to putting a hole in the side of his ship. And put this poster on the wall and remind yourself, am I ignoring the obvious? We want to remind ourselves just one more time, you'll get tired of me hearing you tell you this, is that all risk comes from uncertainty, and uncertainty only comes in two types, reducible and irreducible. And there is a handbook that you should download. You could actually Google it from this phrase, which is NASA's Risk-Informed Decision-Making Handbook. And that's the book that drives almost all of our risk management work where we're involved in a spacecraft or aircraft or any kind of craft that flies or swims or drives, in that we make risk-informed decisions. And in that book, he speaks specifically about these definitions of alleatory and epistemic and ontological. So I'll just remind you one more time about that. So let's look at what we mean when we say epistemic uncertainty. These are the types of exchanges of words that we talk to each other with. If then, if we miss our next milestone, then the project will fail to achieve its business value during the next quarter. Well, that's a risk. That is an epistemic uncertainty. I do not have confidence I will make that milestone. I need to find the root causes of that lack of confidence, and I need to buy them down. I need to pay money to increase the probability of an epistemic uncertainty not impacting my project. There's another one called condition concern, right? Our subcontractor has not provided enough information for us to status the schedule. That's a risk. Well, we can pay money to get better statuses. We can get a different contractor. We can go back and train them. We can do something about this. And then we've got these condition event consequences, right? Our status shows that there's some tasks that are behind schedule. If we miss our milestone, we got a project problem. So now we need a plan B to go fix those. I know about them. They're in the risk register. Let's go fix them. So that's how we talk to each other. And there's a link at the bottom here about how to do that and how to put that into your risk management system. And then this idea that we've got to model the risks. Because without the modeling, we can't have any risk-informed data that allows us to make different decisions than what we're making now. So if all risk comes from uncertainty, we've got to have models that address the probabilistic and the statistical underlying sources of that uncertainty and how they're going to impact cost and schedule and technical performance. So let's look at some pictures here. If I have an alleatory uncertainty, it's a naturally varying outcome of some underlying system. Traffic flow on a highway, how many cars go by every hour or how many cars go by every minute, is an alleatory uncertainty. It's a naturally occurring variance. The weather is alleatory. The delivery and supply chains that are on highways with trucks, especially in our modern world, are an alleatory uncertainty. The epistemic uncertainty is probabilistic. I have a probability of 82% of when I turn on this power system, it's not going to be sufficient to handle the load. Well, I can pay money to find out whether that's true or not, or better yet, I can pay money to get a better power system, to get a bigger power system, to get one that's got 20% margin in it for the original startup load. So we have to separate both alleatory and epistemic uncertainty, and I'm going to show you later on in this little workshop about why that's important and how that actually prevents us using the 5x5 charts that some of the professional organizations want us to do, the risk matrices. The other thing we have to talk about when we talk about risk models is how precise they are. And what is the variance in our estimate? How small is that variance? And then how accurate they are. Is this estimate of the probability that the power will not be sufficient to start up the generators or to start up the pumps that are run by the power generation system? How accurate is that estimate? And how precise is that estimate? And then, of course, how biased is that estimate? This is one of the reasons that professional advice and professional opinions are some of the least reliable and least precise and least accurate opinions about how something's going to either fail or work or not work. We need actual data. And then the next thing with this precision and accuracy and bias is we need to know whether it's a deterministic estimate, that is, I have a number 27 is how many amps it starts on stall to start the pump motor, or is it a probabilistic number? It's 27 plus or minus 20%, depending upon the temperature and the load and the last time the motor stopped. So we got to determine between probability and determinism, and here's an example of doing that. At our systems requirements review, let me use my pointer here, we have this confidence that we're going to make the launch date, right? It's going to be either between June and March. I've got to actually have it working in November of the year before. And then at the preliminary design review, I've got the confidence that we're going to make the launch and the numbers go between May of 2008 and late January of 2008. By the way, this is from a real program of flying to Mars. So this is how NASA works when it does its Mars mission. And then we've got we're getting better here. We've got a probability distribution at the critical design review. And in our manned space or deep space missions, we have a thing called ATLO, which is Assembly, Test, and Launch Operations. And by the time we get to ATLO, we better have a confidence up here in the yellow zone, because, by the way, we're not going to get paid if we don't fly inside this plan here. And then we got Flight Readiness Review, and we've got the confidence that we're in the green now. But we do have some margin because we can show up in between February and November, and it looks like if in February of 08, if we didn't make it, then we missed the launch. So this type of chart shows how it is that we're buying down the risks, we're retiring the risks, we're doing something with the risks to make them go away, or at least get better so we can get our program into the green. And all of this comes from another fundamental model of risk management, which tells us that all the work that we do in our program, as defined in the Integrated Master Schedule, is driven by alleatory uncertainty. So if we're using Microsoft Project or using Primavera P6, and there's a field, a column in that form that you're filling out that says duration, and you type in 47 days, that's actually a most likely number. It's most likely going to be 47 days. The question is, what is the high and the low of that? What is the probability distribution? How low can it go? It can go as fast as 36 days or take as long as 60 days. So those all come from probability distributions for both the cost and the schedule and our capacity for work and our productivity and quantities and activities. So we have this schedule with all these tasks, and each task is actually a random process, and we need to model those random processes. And by the way, I just want to go off topic here real quickly. The PERT formula that has 4 times the most likely plus the pessimistic plus the optimistic divided by 6 is a fake formula. That formula was constructed with the denominator being 6, which is the standard deviation, to convince the Congress of the United States that the Polaris submarine construction would show up on time. And we've got several papers in our references here that speak to that in modern time. So the PERT model, while useful, is not very credible. We want to have a real statistical simulation of our schedule, so it's got to be a Monte-Carlo simulation. And there's lots of papers in our references that tell us how to do that. But just remember, PERT is it's okay as a start, but don't bet a lot of money on it when you're all done. We all know, at least in the United States, that hurricanes come out of the Atlantic, and the National Oceanic and Atmospheric Administration builds models showing the aleatory probabilities of the hurricane hitting your town or your island or your peninsula. So we must think about aleatory uncertainties as the dominant source of risk in everything that we do. And that's essentially what happens when we get going with our alleatory and epistemic schedules and all the technical stuff. So National Oceanic and Atmospheric Administration does all that. The weather people in Europe and in Asia do exactly the same things. They build these models, and all these bands are from their alleatory modeling sources. Cost is the same way. We have to have a cost estimate as the program grows that is driven by epistemic and alleatory uncertainty. And this is a chart from the National Reconnaissance Office, which is a persistent overhead surveillance, which means they're watching everybody at all times, that we work at sometimes about cost. So everything is a random number on any kind of real project. And then we've got some probability estimates of a future impact of a project. So when we talk about there's a 68% probability of the Hurricane Katrina hitting New Orleans within the next 24 to 36 hours with an 85% confidence. So we need confidence on our probabilities. And in our spaceflight business, when we submit the proposal, it has to have an 80% confidence of launching on or before the need date, and an 80% confidence of costing at or below the budget, and that probability itself has to have an 80% confidence. So it's 80 on 80. So I've got an 80% probability of making the launch date, and that number itself has an 80% confidence. And these are actually the words from NOAA. It says 68% of Katrina coming and 85% confidence, evacuate now. Time to leave, time to go. The hurricane's coming. So with that background, let's get to our actual practices. And what we're interested in doing with these actual practices is making risk-informed decisions. That's our role as either a project manager or a program manager or the program management office or whoever is accountable for showing up on time, on budget, with the right solutions so that those that are paid us to do this work are actually happy about it. Here's a little chart that you should put on your wall or put in your notebook for sure, and that is to remind ourselves over and over again that uncertainty is the source of risk. And the irreducible uncertainties are alleatory, naturally varying in ambiguities. The reducible are epistemic, and those are probabilities, and they have impacts, and they have periods of exposure. And then we have ontological. So we don't usually in the project world deal with ontological risks, but a real quick story when our leaders of our country talked about the original Iraq, and Donald Rumsfeld said there were unknown unknowns. He was talking about ontological uncertainties. Turns out that wasn't actually true. If he had read Herodotus, the histories, he would have seen that Herodotus told Alexander the Great in 320 BC to don't go there, and because nobody has ever conquered that part of the world. So we do have ontological uncertainties that are unknown unknowns. The question is, are they knowable? I may not be able to afford to know them, or I may not be able to have enough time to know them, and therefore they are unknowable. So here's a little chart that just reminds us again, we talked about this in our principles section, about what is epistemic uncertainty and what is alleatory uncertainty. And just to remind you that the probabilities occur, the probability modeling in epistemic uncertainty is through a probability distribution function, where I have an integral equation that describes the distribution of all the probabilities. And in aleatory variability, or aleatory uncertainties, I have a probability density function. And that generates all of the random variables. It's a stochastic process. So the weather is modeled with stochastic processes that are naturally occurring, and the failure of a motor to start when commanded to do so is a probability occurrence. And there are two different functions. They're both integral equations, but they have different propositions coming out of them, and different processes for generating them, and different processes for modeling them. So where do we go look for this stuff? Well, the place to start for looking for uncertainties that create risk is our work breakdown structure. So we have a good work breakdown structure when the WBS itself describes the deliverables. The WBS, the work in the breakdown structure, is not work. That's described in the integrated master schedule. It's products or the services that deliver the outcomes. So there's a confusion sometimes when we say WBS. This is not the work. This is the deliverables. It's the product breakdown structure. Here's a little picture from the product breakdown structure of what we would call the WBS of some risks on an actual device. Okay, one of our biggest risks in the spaceflight business is we can't keep the center of gravity inside the spacecraft. People keep sticking things on it, sensors or antennas or arms, and the CG goes outside the center of gravity. The gross liftoff weight is a big risk. You can only fly to low Earth orbit if your vehicle weighs less than 27 metric tons. So if we're in the preliminary design, we've got a CAD model and we've got drawings and we've got cardboard cutouts of everything, and we add it all up and it weighs more than 27 metric tons, we're not going to fly. We're never going to make it to the launch pad. We've got software problems. We've got unattended launch design systems. We've got achieving all the component qualifications. So we need to have a chart like this from the WBS. Over here are the WBS numbers and what they're going to impact. This is a technical impact. This is a schedule impact. And what is my initial risk? Some scoring system. And what is the risk at the integrated baseline review? If you're not in the federal acquisition, that doesn't mean anything, but that's where we ask the customer, here's what we think you want us to build. Is this true? And if the answer is yes, then we can start spending their money. And then, of course, that preliminary design review, we've got to get everything into the yellow, if not green, because there's no rational way to move forward on the design and the bending of metal or the pouring of concrete if we don't know what done looks like. So this is a very simple little chart, and this is all contained in the risk register. And I'm going to leave this up for just a second, but it'll be in your slides. This is the content of a credible risk register. Now this content comes from our Department of Energy, which is actually not about energy. It's only about 18% about energy in terms of their budget. The other percentage is about nuclear weapons for the National Nuclear Security Agency, where I had a career at a weapons plant. But this is the minimum content of a risk register. So this will be in the handouts at the end, but make sure your risk register has every one of these items in it. Otherwise, it's not a risk register. It's just a list of all the things that are going to go bad. So when you have that items in the risk register, then what we can start doing is asking ourselves, which ones are alleatory and which ones are epistemic? What is the category? What is the status? What is the success metrics for the risks? What do we have metrics to avoid things? What are these risks? Are all these risks alleatory? They're naturally varying, or are they epistemic? They're probabilistic, that I can pay money to make them go down. So that's the question that we need to ask with the risk register. And when we have that information, we can now start dealing with our alleatory uncertainties, because we can't make them go away. We can't pay money to test it, to build it stronger, to buy two in case one breaks, to install redundancy, whatever we want to do. We've got to have margin. We've got to have schedule margin, and we have to have cost margin. And in our world, the cost margin is called management reserve, and it's released by management. And the schedule margin here is in the schedule. It has no money on it. It has no resources on it, but it protects the delivery of the items here. We actually need them somewhere down the road here. And we've run our Monte-Carlo simulation, and we found out that there is some probability that we're not going to make it. So this is our 80% confidence number, and we need to put it in a plan B. And what margin we don't use, that is, we do actually show up earlier here, we can move to the future. And that way we don't have to give that away. We can have our margin. So in our world of flight systems, we've got to have an 80% confidence of showing up on or before the launch date, and the schedule has to show where all that schedule margin is and how we manage to it every day. And what we do is we have a chart that is the schedule margin burn down chart, and it looks like this. This is essentially a risk score, but that would be part of the uncertainties from the WBS that create risk, that reduce the thing, and we've got to burn these down as we go. So this is a fairly long program. This is a manned spaceflight program, started in 2005 essentially, and it was supposed to fly in 2011. Hasn't flown yet. Elon Musk and Bezos have beat us to it in terms of NASA, but you got to have this chart. And then these items, these 1 through 23, are the specific activities that took the risk from red to yellow to green. And that's part of the reporting of progress to plan for keeping the spacecraft inside the center of gravity limits. That is, the CG of the spacecraft is actually inside the spacecraft. Otherwise, it's unstable. So for whatever your key deliverable and key risk, CG would be 1, or whatever it is, you need a chart like this that shows how it is you're going to burn down the risks, where these are in the schedule, what are the units of measure for showing that you went from this level down to this level, and then we stayed here for a year, and then we went down to this level till we get to green, and then how to keep it green. Keep the program green is one of the phrases we use all the time. The other little story is keep it inside the white lines. If we're driving our car, it's real simple. Teach your kids, stay inside the white lines, you'll be safe. So we've got to have a chart like this in terms of a practice. Somebody has to come look at these, and these are usually reportable monthly. And then here is a formal process that we use in our U.S. Department of Defense at acquisition of all of the activities that go into our risk management process. We got to have a plan. We got to assess the plan. We got to have handling strategies. We got to have monitoring. We got to identify them. We got to analyze them. It's a closed loop feedback system, and we got to have documentation at all times. So owning a risk register or owning a spreadsheet that's calculating the risks is necessary but not sufficient. And you can download there's a current version of this. This was 5th edition. There's a few new ones. But you got to have all of these steps, otherwise you're not doing risk management. When you're doing these steps, so using our loop of identify, analyze, plan, track, control, and communicate, here's a little flow chart that you can use to put that to work. You've got to come up with objectives. You've got to come up with a hierarchy and the technical performance measures for each of those deliverables and what risks are going to jeopardize their success. And you've got to come up with some proposals and identify the alternatives to those, either the corrective or preventive actions or even an alternative design. Do the risk analysis for that and deliberate whether that risk analysis is actually going to be successful in reducing the risks or preventing outcomes. Then you got to track it, and the key is all the stakeholders have to be involved, all the design processes and all the people around them have to be involved, and all the technical planning impacts and the decision analysis for the planning and the scheduling are involved. And the result is we have a risk-informed decision-making process that we follow every day, every week, every month, at whatever period you need to make sure that lateness or over budget or technical low performance is not a surprise. We've all seen these risk matrices. They're everywhere. Rate your probability of occurrence 1 to 5, rate your probability of impact 1 to 5, do some red, green, yellow, make a nice matrix, call it done, we're doing risk management. It turns out, of course, that The probability of occurrence is actually either a probabilistic function, the one below is a Poisson distribution, or it's a stochastic process function, a probability density function for the weather or water flow or whatever has to do with that. And the impact is the same. So we cannot do mathematics with these. We can only model them either with Monte Carlo or some other statistical processing tools. Method of moments is another one that we use. But we cannot do arithmetic. We cannot multiply them or add them. And so here is a simple way to do a qualitative one, but not have to do the math, is to define what it means to have a 1, 2, 3, 4, 5 and have a 1, 2, 3, 4, 5. 1 is not likely. It's just not going to happen. And 5 is it's going to happen. It's guaranteed to happen. And the same thing for the consequences. Minimal impact all the way to catastrophic impact. But I'm here to tell you, do not do mathematics on these. And there's going to be some papers at the end. Tony Cox, he's actually a professor at our university here in Boulder, Colorado, construction professor, has got some really good papers on the fallacies of risk matrices. So here's a real risk matrix that is qualitative, not quantitative, for a drug analysis for Ebola virus. So you can do this if you do it this way. So the intersection of this likelihood, and by the way, the way out of that is to change the numbers from 1 through 5 to the letters A, B, C, D, E, so you can't do arithmetic with it. It prevents you from doing arithmetic. So we decided that the Federal Drug Administration requires additional toxicology and or some analysis steps and studies, and it's likely going to occur, and it's going to have moderate impact on our program. So we're going to give it a yellow. Or here's one. The FDA mandates that aerosol exposures via viral challenge experiments to be performed on non-human primate efficacy studies. By the way, this is for Ebola virus. This is to develop a vaccine for Ebola. It's got, a moderate impact here on the likelihood, and it's got a moderate consequences if it doesn't work. Here's some reds, right? The general practices compliance with the biosafety level 4 required for the animal rule. Well, we don't have a lab that's bio-level safety 4 certified. So we're going to have to spend a whole bunch of money to go build a lab. This was up in Seattle, Washington, to make that happen. So you can use the 5x5 charts to answer and quantify or qualify, not quantify, qualify these types of risks. So that's the way to use the 5x5 charts. Then what we've got here is we've got a qualification solution on in its problems with that. So this little chart just replicates the same thing. We've got to identify all the stuff. We've got to rate it. You would change these 1 through 4s to A, B, C, D, E, and then you would put all the high, mediums, and lows, and you could come up with some phrasing or phasing or analysis of which risks are higher than the other risks, and in terms of a qualification, which ones should we go work on first. But this is not risk quantification. There's no numbers in there that you can make decisions on other than to take the next step to go find out what those numbers are. To do that, we have to do quantification. So now we've got to make models, usually Monte Carlo models. There's several other methods. Methods of moments are one. Design structure matrix, coupling and cohesion models are one. There's a bunch of things around. But then we can do these real estimates with actual numbers, with quantitative numbers. Then in the Monte Carlo simulations, we can actually do arithmetic between probability distributions. This distribution times that distribution equals that distribution in my Monte Carlo simulation. Then we can produce a nice chart, and then we can make qualitative verifications through our quantitative numbers. And I want to introduce Tim Lister again if we hadn't heard enough about him, and that is that this is how adults manage projects. So risk management is how adults manage projects. And here is a link to the problems with risk matrices using what are called ordinal scales. Ordinal numbers are relative to each other. 2 is twice as big as 1. 3 is 1.5 times bigger than 2. Things like that. Those are ordinal numbers. In our engineering risk management world, we want cardinal numbers. I have an 87% probability of showing up at the launch pad on time with an 82% confidence of that 87% probability. That's good enough for us to win the job. When we're 4 months away from launch, it better be up in the high 90s. And of course, 2 days before launch, it better be at 100, or otherwise we're not going to make it. But this is the link here to go do that. And if you're not familiar with this archive, this is hosted by the Los Alamos National Laboratory, and it's a complete library full of scientific and engineering papers and documents that's open to the public. So go there and search for almost anything you want. So here's our problem with risk modeling, right? We think that we've got a symmetric distribution, a Gaussian distribution, for example, or a Poisson distribution. And by the way, the Gaussian distributions, when someone say there's a normal distribution, that only occurs if each variable in the distribution is identical and identically distributed. It's called IID. They're independent and they're identically distributed. Air molecules in a jar that you're boiling to make steam are identical and independent. Nothing else on a project is identical and independent. So when you see symmetric Gaussian normal distributions, those are never true. Okay, so let's go look and see what we have to do about this. So we want 3 steps to get our mandatory risk. We want high quality projects and products and processes. That's kind of restating the obvious. And we start with a contingency-free estimate, and then we do the risk analysis. So we want something that assumes to work in the absence of any risk. It's risk-free. What's it going to take if nothing goes wrong? We got every resource we need, it's all properly formed, it's got no constraints, and it's completely unbiased on our duration estimates. Start out with that schedule or that cost estimate. And then what we'll do is we will put the risk analysis on the top of that. What is the likelihood of the project's cost and risk can be met? I've got this cost target that had no risks. What is its probability of showing up with that cost? Oh, I don't know, after we do the analysis, it's 42%. We have a problem. Or what is the probability of showing up on time in this risk-free schedule? It does show that we can make the launch date 4 years from now at the launch site in Northern California at Vandenberg Air Force Base. But when I run my Monte-Carlo simulation for the naturally occurring variances in the duration, it shows I'm 11 months late. I only have an 80% chance 11 months from now. So we need a new schedule. That cost and schedule modeling is called the joint confidence level. It usually is not seen in the construction world because a lot of that stuff is firm fixed price, and this is the 30th time they've done the freeway repaving, so they got fairly low risk except for the weather. But in any kind of discovery design project, you want the joint confidence of showing up on time and on budget. So here's the way to do that. I've got a schedule, I've got my risks, I've got my costs laid out. Here's a chart of putting those together. Here's some final cost date and some final finish date, and I want to be to the left and below of this line right here. I want to keep it green. So there are tools that will make this picture for you when you do the Monte-Carlo simulations of the costs and of the schedule and put them together. So I've got to show up on time and on budget and having it work. Otherwise, we get to read about ourselves on the front of the Washington Post. and that's not very pleasant. So there's a bunch of references in the back that show how to do this and all the tools that do that. And here's the little process to put it all together. I start with my risks, and I do them in a qualitative manner with letters here, very low to very high, no numbers. I prevent multiplying or adding numbers. Collect all the data, assign all the likelihoods, map all those to the schedule, and in my schedule I collect all the schedule, I determine the high level flow, I do all my good scheduling. And then the same thing for the cost data. I put it all together, I collect all the costs, I get a credible basis of estimate, and I put all that in the schedule. Then I assess all the probabilities for the durations. That's an alleatory uncertainty modeled with Monte-Carlo. And then I assess all the uncertainties to the cost, which is also an alleatory uncertainty. And then I run the tools, I incorporate all those into my schedule, and I validate that file, and I run the analysis. And what I get is this. I get some curves that say, here's where the cost is going to be with the understanding of the schedule that I have and its alleatory uncertainties and the handling strategies for those alleatory uncertainties. And here is my schedule model. And that's for the schedule relationship. So these are the cost entity relationships, and these are the schedule entities relationships. It's usually the non-critical path items that cause us problem. If it's on the critical path, we know it, we see it, we're handling it. It's the stuff that comes out of nowhere that wasn't on the critical path that then shows up on the critical path that we have no plan for. And we get these nice charts that here's our cost uncertainty and here's our schedule uncertainty. And we can then decide, what does it have to be by what date? How confident do we have to be? How much money do we have in reserve? And how much time do we have in reserve? And do we have to have a new plan? We're not going to make it if we keep going. And so this is the outcomes of those things from a practice of putting all those tools together. So I want to go through I don't want to read these to you, but here's a bunch of things that can go wrong, right? We're about at our 50-minute time here. We depend on the processes too much. We lack continuity. We're over-reliant on a tool. We don't pay attention. We don't have vigilance. We don't have actual questions about the automatic mitigations. We think everything's going to be fine. We're going to fix the risk by just changing something real quick here, and we'll get back on schedule by patching the software or building something else real quick. We do all of those things in error because we don't have the top-down, bottom-up strategy. We have to work from the bottom and the top. We don't have early planning. We don't have analysis limitations. In other words, what are the limitations of our analysis? What analysis tells us and what analysis can't tell us. And we've got to have good structured monitoring. We've got to make this a profession. And we've got to update the risk database frequently. I've worked a couple of big jobs on big weapon systems that we update the database every day. At the end of the day, what new risks appear. So this is the way to get out of this. Here's a link to good systems engineering kind of stuff to do that. And of course, here's our real problem, right? We talk about regression to the mean, that is the average temperature. So here's a quick little analogy. I'm going to pick somebody, I'm going to pick Alexi, and I want to send him to Trinidad, Tobago with a hat and a clipboard and a chair, and he's going to write down the high temperature of the day for 1 year. And he's going to come up with what is the most recurring number of the high temperature of the day. And it turns out that number is 84 degrees. Okay, now I'm going to send you to Cody, Wyoming, which is only about an hour and a half north of us, with a chair and a hat and a pen and a clipboard and maybe some other things to keep you warm. And you're going to write down the number, the high temperature of the day for 365 days. The most recurring number, the most likely number to appear out of all that distribution is the same. It's 84 degrees. It appears much less frequently, and therefore you cannot do regression to the mean or regression to the mode. It's the long tails that cause the problems. This is why the PERT formula is bogus, because the minimum times 4 times the most likely plus the maximum divided by 6 does not work in the presence of uncertainties, period. So regression to the mean means we're going to fail. And there's our little dinosaur. Okay, we're right at the 51 minutes, and here's our problem in the end, is that we got to look after the black swans. By the way, black swans are common in the parks in Sydney. They're not common in the US or Europe, but it's an event that happened that we didn't see coming. So that's what usually causes the big problems here. I'm going to leave this up for a second. It'll be in your hard copy, but here's the links to all the materials that I've gathered over 43 years of doing this. But just make sure that when you click on this blog thing, it takes about 15 to 20 seconds to get you to each of these, so you can do that. All right, we went a minute over, but hopefully everybody's got what they need, and please do not hesitate to call me or text me or send me an email, and we'll provide all the other stuff that we need.